maybe the same intensity as this CH here, be very pointy. It would be pretty much at the same location, but it would only come down to maybe somewhere in this box here. It's not going to come all the way down to the bottom there. Right, and then we come to the last one, which is the 2-bromobutane. This one is thoroughly boring. There's nothing to label except the CHs that are over here, and so you kind of just find it by process of elimination, or that you expect to see nothing interesting at all in this spectrum. So just to kind of run over what this thing is here. So this unit here, this is a benzene ring. Now it is something that you'll become thoroughly acquainted with in year 13. And it's a very, very important structure. If you look up the structures of chemicals that you come into contact with every day, say you look up the structure of paracetamol, you'll see this structure inside it. It's very, very common in biological systems, in loads and loads of drug molecules. So the chemistry of benzene is one that's very important and a very interesting thing to study. Now, benzene is something called an aromatic ring. And so the bonding is not single, double, single, double, single, double, which is what's implied by this here. And this diagram here is something called the Kekule structure, which was proposed by some chemist with the surname Kekule, because the chemists knew about this C6H6 molecule that they called benzene, but they couldn't work out a reasonable structure for it. And this was the first structure proposed that was kind of quatonatol. It's not entirely correct, but it's really, really close. But this diagram is very commonly still used by chemists, as it's very useful for drawing mechanisms for reactions. So the curly arrow things. The thing you're going to use at A level, which if we were doing stuff on the whiteboard I'd normally use, but none of the images online have this. This is what at the A level consider the better diagram, and in many ways it does more accurately represent the structure of benzene. Which is that we've got this continuous bonding, this ring that goes round, and so it's completely symmetrical around. There's no difference between any of the bonds. So the bonds between each of the carbons are identical, whereas the Kekule structure makes it look like it's not. So to delve in even further with what's going on, in a regular double bond between two carbons, you've got some p orbitals. So the p sort of subshell or orbital, and the ones that point up and down, they overlap with each other to form a region of electron density above and below, and that forms the bond. So this forms a new orbital instead of these orbitals that the electrons then occupy. And so typically we can think about maybe one electron from each. We form two new orbitals. This is one of them. This is called the bonding orbital, which both of those electrons are going to go into, and that helps glue the two, it sort of attracts the two nuclei together, forming a bond. There's actually the anti-bonding orbital, so this is the constructive interference for people doing physics and their waves, the destructive interference forms orbitals out here, and so the electrons occupy the space apart from these, on the outside of where the two nuclei are, and that actually pulls it apart. So it's the opposite of bonding, it is anti-bonding. So this is caused by the overlap of these p orbitals. The electrons won't occupy this regularly, as this is very, very high energy, whereas this is lower in energy, it's more stable than the electrons being on their own in the individual orbitals on the atoms, and that's the fundamentals of how bonding occurs between every atom. Now in benzene, we sort of reach a point where it kind of loops back around on itself from all of these p orbitals. So we've got these 6 carbons arranged in a hexagon, so they're completely flat, and we've got the p orbitals protruding up and down. Now, if we just look at 2 carbon atoms on its own, we've got the same setup as over here, and so they could maybe just form a double bond between the 2 carbons that are next to each other. So these 2 could pair up, these 2 could pair up, and these 2 could pair up, and that would give us the Kekule structure. But actually, every orbital overlaps with both of its neighbours, and we form a large ring system. So these all overlap, and so we form sort of a almost like a donut shape of electrons going around the top and around the bottom. And so we just simply do not have a regular double bond. And so when we look at the, if we look at the IR spectrum, we simply don't have a regular double bond. It's not the same as an alkene. And this is why benzene is interesting, because it reacts very differently from a regular double bond. So if we take cyclohexene, I just had delivery. So if we take regular cyclohexene, if we react this with bromine, you'll get electrophilic addition across this double bond. You don't have to do anything special, you don't have to heat it up, you just mix them together and they'll react. So just like with ethene, one of the first reactions that you looked at. So we'd end up with 1,2-dibromohexane, a cyclohexane, and so just a regular electrophilic addition reaction. But if you try and do this with benzene, so if I just do the Kekulé structure, this does not react with bromine. So you put this with Br2, and under regular conditions it does not react with it. This is much more stable. With just the single double bond, it's highly reactive in the presence of bromine. These two are very reactive with each other, and so it just goes ahead at room temperature, whereas this doesn't. So they're very drastically different from each other. Even though kind of on paper, when you look at here, you might think they're very closely related. So it's a completely reasonable mistake to make. It's not a criticism at all, and it's not something that's going to come up in infrared questions generally. And the only reason that's on there is it's the only infrared spectra it was just one I could find easily that had an NH2 group in to test you on that.